There's something strangely captivating about Mars, something that has pulled human curiosity toward it for centuries, almost like a silent invitation hanging in the night sky. That faint red glow you see isn't just another star. It's a world that civilizations long before us named after gods of war, a place that storytellers filled with imagined canals and alien life, and now, a destination we are seriously planning to reach. Today, figures like Elon Musk speak confidently about building cities there, while organizations like NASA outline missions to send humans across millions of kilometers. Companies such as SpaceX are even designing spacecraft specifically for this goal. The message sounds bold and clear. Mars is next, and humanity is ready to become a multiplanetary species. It's an idea that feels powerful, almost inevitable, and honestly, it's something many of us want to believe, because at its core, the dream of stepping onto another planet speaks directly to something deeply human, the desire to explore, to push beyond limits, to go further than we ever have before. But here's where the story takes a turn that most people don't expect, and it's important to truly take this in. Reaching Mars, actually sending humans there, bringing them back safely, and especially building a lasting settlement, might not just be difficult. It might be impossible. Not impossible in the sense of being challenging or requiring better technology, but impossible in a much harsher sense, where the laws of physics, biology, and engineering simply don't allow it, at least not with anything close to the tools we currently have or can realistically expect in the near future. That may sound extreme, but this isn't about pessimism or trying to go against popular ideas. It's about looking at the numbers, understanding the science, and following where the evidence leads. When you break down the physics behind a mission to Mars, when you calculate the energy required, consider radiation exposure, and examine the engineering demands, the scale of the challenge becomes overwhelming. Mars may seem close, especially since it's our neighboring planet after Venus, and visible even without a telescope, but appearances can be misleading. That closeness is an illusion, and in reality, Mars may remain forever out of reach. To understand why, we need to start with something simple: distance. At first glance, Mars doesn't seem that far away. It's right next door in cosmic terms, orbiting the same sun as Earth, but the numbers tell a very different story. The distance between Earth and Mars changes constantly because both planets move in elliptical orbits. At their closest point, known as opposition, Mars is about 55 million kilometers away. At its farthest, when the planets are on opposite sides of the sun, that distance stretches to roughly 400 million kilometers. That's not a small difference. It's a factor of 7, which means timing is everything. Missions can only launch during specific windows that occur about every 26 months. And if you miss that opportunity, you're waiting more than 2 years for the next one. To put this into perspective, consider the Moon. It's only about 384,000 kilometers away from Earth. That means even at its closest, Mars is roughly 140 times farther than the Moon. And yes, we reached the Moon multiple times between 1969 and 1972. With 12 humans walking on its surface, so it might seem logical to assume that with modern technology, reaching Mars should be achievable. But that assumption overlooks a critical truth, and that truth changes everything. Part 2540 words. The reality is that distance in space isn't just about how far something is, it's about how much energy it takes to get there. And this is where the comparison between the Moon and Mars completely falls apart. Traveling through space doesn't involve air resistance like it does on Earth, but it does involve something far more demanding: gravity. To leave Earth, a spacecraft must overcome the planet's gravitational pull, and once it's in space, it must navigate the gravitational influence of the Sun while moving between planetary orbits. At the center of this challenge is a concept known as delta V, which simply measures how much a spacecraft needs to change its velocity to complete a mission. This number directly determines how much fuel is required, and that relationship is governed by something called the rocket equation, first described by Konstantin Tsiolkovsky. For a mission to the Moon and back, the required delta V is about 15 kilometers per second. That alone is enormous, involving speeds far beyond anything we experience in everyday life. But for Mars, the required delta V jumps to somewhere between 30 and 40 kilometers per second, depending on the chosen trajectory. At first, doubling that number might not sound too bad. You might think it simply means doubling the fuel, but the rocket equation doesn't work that way. Instead of increasing fuel needs linearly, it increases them exponentially. That means doubling the delta V doesn't just double the fuel requirement, it can multiply it several times over. The reason is simple but brutal. Fuel itself has mass, and that mass needs to be accelerated along with the spacecraft. So you need fuel to carry fuel, and then even more fuel to carry that additional fuel. it quickly becomes a cycle that spirals out of control. As a result, spacecraft end up being mostly fuel. In many cases, 90 to 98% of the total mass is just propellant, leaving only a tiny fraction for everything else, including the crew, life support systems, and equipment. Even during the Apollo missions, the massive Saturn V rocket weighed about 2.8 million kilograms at launch, yet less than 2% of that mass was actually carrying the astronauts, and that was just for the moon. A mission to Mars would require something even larger and more complex. You might argue that modern technology should solve this problem, and to some extent, it helps. Today's engines are more efficient than those used decades ago, but the improvements are gradual, not revolutionary. We still rely on chemical rockets, burning fuel to produce thrust, just like in the 1960s. More advanced propulsion systems do exist in theory and early development. Ion engines, for example, are extremely efficient, but produce very low thrust, making trips take years instead of months. Nuclear propulsion offers more power but comes with serious technical, political, and safety challenges, and hasn't been fully developed for human missions. So for now, we remain limited by the same fundamental physics. Chemical rockets, bound by the rocket equation, make Mars missions extraordinarily difficult. But fuel isn't the only problem. Time is just as critical, and unlike a 3-day journey to the moon, reaching Mars takes months. Using current technology, the most efficient path, known as a Hohmann transfer orbit, takes between 6 and 9 months just to get there. And that's only the beginning of a much longer journey. Because once you arrive near Mars, the mission doesn't simply end or turn around. You can't just land, refuel quickly, and head back home. The positions of Earth and Mars are constantly changing, and after reaching Mars, astronauts would have to wait for the planets to align again for the return journey. That waiting period alone can last between 12 and 18 months. Add another 6 to 9 months for the trip back, and suddenly you're looking at a mission lasting roughly 2.5 to 3 years. Now think about what that really means. You're asking a small group of astronauts to spend years inside a confined spacecraft, far away from Earth, with no realistic option for rescue if something goes wrong. On the International Space Station, astronauts have stayed for up to a year, but even that environment is nothing like a journey to Mars. The station orbits just a few hundred kilometers above Earth. If there's an emergency, crews can return home within hours. Supplies are regularly delivered, including food, water, and spare parts. None of that exists on a Mars mission. Out there, you are completely alone. If a system fails, you fix it with whatever tools and parts you brought, or you don't survive. If someone gets seriously ill or injured, there is no evacuation. There is no backup crew. There are no supply missions coming to help. And one of the hardest truths to accept is this: the return journey is even more complicated than the trip there. To come back to Earth, you either need to carry all the fuel required for the return trip from the very beginning, or you need to produce it on Mars. Carrying it from Earth dramatically increases the spacecraft's mass, making launch even more difficult due to the same exponential fuel problem we discussed earlier. Producing fuel on Mars sounds like a solution, but it introduces an entirely new layer of complexity. It would require sending advanced chemical processing equipment ahead of the crew, landing it safely, and ensuring it works perfectly without human supervision. And that's exactly what mission concepts from NASA currently suggest: sending cargo missions first, delivering habitats, supplies, and fuel production systems before astronauts even leave Earth. This reduces the load on the crewed spacecraft, but it also means multiple launches, multiple landings, and multiple systems that all need to function flawlessly. If any one of them fails, the entire mission could be at risk before it even begins. Complexity becomes the enemy here. Every additional component introduces another point of failure, and in space, failures are rarely minor. They are often catastrophic. The more moving parts you have, the higher the chance that something goes wrong, and when it does, there's no easy fix. Then there's the question people often ask: why not just travel faster? If the journey takes too long, why not develop engines that can shorten the trip? It sounds simple, but the physics make it incredibly difficult. To cut travel time significantly, you need to reach much higher speeds. And reaching higher speeds requires far more energy, which again means far more fuel. The rocket equation doesn't allow shortcuts. There's also another problem. If you accelerate faster to reach Mars quickly, you must also slow down when you arrive. And slowing down from high speeds requires just as much energy as speeding up in the first place. On Earth, returning spacecraft use the atmosphere to help slow down through friction, but Mars presents a different challenge entirely. Mars does have an atmosphere, but it's extremely thin, only about 1% as dense as Earth's. That means it's thick enough to generate intense heat during entry, but not thick enough to slow a spacecraft down effectively. So even after enduring the heat of atmospheric entry, a spacecraft still needs powerful engines firing in the opposite direction to reduce its speed enough for a safe landing. And this isn't a small object we're talking about. Landing a robotic rover is one thing. Landing a massive crewed spacecraft carrying life support systems, habitats, equipment, and return fuel is something entirely different. The largest object we've successfully landed on Mars so far is the Mars Curiosity rover, which weighs about 1 ton. A human mission would require landing payloads tens of times heavier, possibly 20, 50, or even 100 tons. That scale introduces engineering challenges we have never fully solved. Companies like SpaceX are developing systems like Starship, which aim to deliver massive payloads to Mars. But these systems are still unproven in real mission conditions. Everything has to work perfectly on the first attempt, because on Mars, there is no second chance. Even if we overcome the landing challenge, another hidden difficulty appears: communication delay. Space may seem empty, but it is vast beyond intuition. Signals travel at the speed of light, which is incredibly fast, about 300,000 kilometers per second. Yet even at that speed, communication between Earth and Mars is slow. When the planets are closest, it takes about 3 minutes for a signal to travel one way. When they are farthest apart, that delay can stretch to 22 minutes. This creates a round-trip communication delay of up to 44 minutes. That means real-time communication is impossible. During critical situations, astronauts cannot rely on immediate guidance from mission control. They must make decisions on their own, often under extreme pressure, knowing that any mistake could be fatal. This delay already affects robotic missions. Rovers like Curiosity and others are not controlled in real time. Instead, engineers send a sequence of instructions, wait for the rover to execute them, and then analyze the results. It's a slow, careful process. For humans, this delay means something much more serious. The crew must be prepared to handle every possible emergency independently. They need to be engineers, doctors, mechanics, and scientists all at once, carrying every tool and spare part they might need because help is simply too far away. And then there's the psychological challenge, something that is often underestimated but could be just as critical as the physical obstacles. Spending 3 years in isolation, confined to a small space with the same few people, knowing that Earth is tens of millions of kilometers away, creates intense mental strain. Studies from submarines, polar research stations, and isolation experiments show that long-term confinement leads to stress, conflict, and declining performance. The difference is that in all those cases, there is always a way out. On a Mars mission, there isn't. Once you leave, you are committed. There is no turning back halfway through. Some research suggests that after about 18 months, psychological performance can begin to decline significantly. But we've never tested humans in isolation for a full 3-year deep space mission. In many ways, such a mission would be an experiment with human lives at stake. And all of this comes before we even address what might be the most dangerous challenge of all, the one that could make everything else irrelevant. The problem that stands above every other obstacle, and the one that brings us directly into the next part of this story: radiation. Now we arrive at the problem that changes everything, the one issue that doesn't just make a Mars mission difficult, but potentially impossible: radiation. Not the kind you hear about in everyday life, but deep space radiation. Constant, invisible, and deadly, in ways that are hard to fully grasp. On Earth, we are protected by 2 powerful shields: our atmosphere and our planet's magnetic field. Together, they block or deflect most of the harmful radiation coming from space. But the moment you leave low Earth orbit, that protection disappears. Astronauts traveling to Mars would be exposed to 2 main types of radiation. The first is solar radiation, bursts of energetic particles released by the sun during solar flares and coronal mass ejections. The second, and far more dangerous, is galactic cosmic radiation, high-energy particles originating from outside our solar system, traveling at nearly the speed of light. These particles can pass through spacecraft walls, through human tissue, and even through DNA itself, causing damage at the cellular level. On missions to the International Space Station, astronauts are still partially protected by Earth's magnetic field. Even then, they receive significantly higher radiation doses than people on the ground. But a journey to Mars would take astronauts far beyond that protective zone for years. During that time, they would be continuously exposed. The numbers are alarming. Current estimates suggest that a round-trip mission to Mars could expose astronauts to radiation levels close to or even exceeding the lifetime limits set for space crews. And that's under normal conditions. A major solar storm during the journey could deliver a dose high enough to cause acute radiation sickness, potentially within hours or days. Without proper shielding, it could be fatal. So why not just build better shielding? That seems like the obvious solution. But here again, physics pushes back. Effective radiation shielding requires mass, thick layers of material like water, metal, or specialized composites to absorb or deflect incoming particles. But adding mass makes the spacecraft heavier, and as we've already seen, more mass means exponentially more fuel. It's the same trap all over again. There are ideas being explored, like using water tanks as protective barriers, or designing spacecraft with dedicated storm shelters where astronauts could hide during solar events. Some researchers are even studying artificial magnetic fields to mimic Earth's protection. But none of these solutions are fully developed, and none have been proven for long-duration human missions in deep space. The harsh reality is that we don't currently have a reliable way to protect humans from prolonged exposure to deep space radiation. And this isn't just about short-term survival. Radiation increases the risk of cancer, damages the nervous system, affects cognitive function, and may even lead to degenerative diseases over time. In other words, even if astronauts survive the journey, the long-term consequences could be severe. And here's the deeper issue. Radiation doesn't just threaten the crew during the journey. It also affects any idea of building a permanent presence on Mars. Unlike Earth, Mars has a very thin atmosphere and no global magnetic field. That means its surface is constantly exposed to radiation. Living there long-term would require habitats buried underground or heavily shielded structures, adding yet another layer of complexity to an already overwhelming challenge. So when people talk about colonizing Mars, about building cities and making it a second home for humanity, they often overlook this fundamental problem. It's not just about getting there. It's about surviving there, day after day, year after year, in an environment that is fundamentally hostile to human life. And yet, even if we imagine that somehow we solve the radiation problem, even if we find a way to protect astronauts during the journey and on the surface, the story still doesn't end there. Because reaching Mars safely is only half the battle. Staying alive once you arrive introduces a completely new set of challenges, and some of them are even harder to overcome. Let's assume, for a moment, that everything works. The launch goes perfectly, the journey through space is successful, the crew survives the radiation exposure, and the landing on Mars is flawless. After months in transit, humans finally step onto the Martian surface. It would be one of the greatest achievements in human history. But almost immediately, a new reality sets in. Mars is not just another place. It is an environment completely incompatible with human life. The atmosphere on Mars is incredibly thin, about 1% of Earth's, and composed mostly of carbon dioxide. There is no breathable air. Temperatures can drop to minus 60 degrees Celsius on average, and even colder at night. Dust storms can cover the entire planet, lasting for weeks or even months. The surface is dry, barren, and exposed to constant radiation. That means astronauts cannot simply walk outside without full protective suits. Every breath of air, every drop of water, every bit of food must either be brought from Earth or produced using complex systems that must work perfectly at all times. Life support on Mars isn't just important, it's everything. If it fails, even briefly, the consequences are immediate. Habitats would need to be pressurized, insulated, and shielded. They would have to maintain stable temperatures, recycle air and water, and protect against radiation. Building such systems on Earth is already difficult. Building, transporting, and operating them on another planet millions of kilometers away is far more challenging. There's also the issue of gravity. Mars has only about 38% of Earth's gravity. We know that long-term exposure to low gravity, like on the International Space Station, causes muscle loss, bone density reduction, and other health problems. We don't yet know how the human body would respond to Martian gravity over years. It might be enough to prevent some of these effects, or it might not. The truth is, we simply don't have the data. Then there's the question of resources. Water may exist on Mars in the form of ice, and there are plans to extract it. Oxygen can potentially be produced from carbon dioxide using chemical processes. Fuel might be created using local materials, but all of these systems require advanced technology, precise operation, and constant maintenance. If any one of them fails, the entire mission could be at risk. And remember, there is no backup. No resupply missions arriving every few weeks. No quick return option if something goes wrong. Every tool, every spare part, every piece of equipment must either already be there or be improvised from what is available. The margin for error is almost zero. Even communication with Earth remains limited, with delays of several minutes each way. That means astronauts must operate largely independently, solving problems on their own in real time. The psychological pressure of that responsibility, combined with isolation and confinement, would be immense. But perhaps the most daunting part of all is this. Leaving Mars might be harder than getting there. To return home, astronauts must launch from the Martian surface, reach orbit, and then travel back to Earth. That requires a fully functional rocket, enough fuel, and precise timing. Any failure in that process means they are stranded permanently. So even in the best case scenario, where everything goes right, a mission to Mars remains an incredibly fragile endeavor. It is a chain of events where every link must hold, because if even one breaks, the consequences are final. And when you look at the full picture, from launch to landing to survival and return, it becomes clear that the challenge isn't just reaching Mars. It's surviving every step of the journey in an environment that gives you no second chances. When you step back, Mars stops looking like the next step and starts looking like a chain of risks where nothing can fail. Yes, NASA has landed robots like Mars Curiosity rover and Mars Perseverance rover. But robots don't need air, food, or a return trip. Humans change everything. Life support, radiation protection, and safe return make the mission far more complex. Each added system increases weight, fuel, and risk. This isn't just engineering, it's physics. Progress alone may not be enough. Real breakthroughs are needed. So when figures like Elon Musk predict Mars missions soon, it raises a serious question. Is it realistic or just ambition? Mars isn't just a goal, it's a limit we may not yet be able to cross.